Organizations are constantly asking questions. How many people left last year? Are men and women represented equally in leadership? Is that new wellness program we launched, is it actually working? Every company is full of questions just like these. And the answers? They're usually hidden in plain sight, right inside their own data. And the key to unlocking all those answers is a powerful tool: statistics.
But think about it. How do you go from this mountain of raw numbers, attendance records, survey results, performance reviews, to a confident yes or no? I mean, you can't just guess, right? You need a specific toolkit, one that's designed to find the real story hiding inside all that data.
And that toolkit is statistics. So in this explainer, we're going to break down the foundational statistical concepts you need to understand how we can use data to make smarter, fairer, and way more effective decisions about the workplace. Think of this as a data detective's journey. We'll start with the basics: what statistics really is, this mix of art and science. Then we'll learn how to describe the data you have versus making educated guesses from it. We'll cover the right way to sample, how to test your big ideas, and even how to predict the future. And finally, we'll wrap it all up with the potential pitfalls and the key things you need to remember.
All right, let's kick things off. Section 1, Statistics, the artful science. Because, and this is so important, it's about so much more than just crunching numbers.
I love this slide because it really shows the two sides of statistics. On one hand, you've got the science. That's the rigor. It's knowing exactly which statistical test to run, calculating an average perfectly, or designing a survey that's fair and totally unbiased. But on the other hand, you have the art, and that's what makes the science powerful. The art is telling a compelling story with your results, designing a chart that a busy executive can get in like 5 seconds, and presenting your findings in a way that actually inspires people to make a change. You need both. You absolutely need both.
And this whole idea of art and science is the perfect setup for the two main branches of statistics: describing versus inferring. This really boils down to the difference between what your data is telling you directly versus what it suggests about the bigger picture. So first up, you've got descriptive statistics. The best way to think about this is the what happened report. It's all about summarizing the data you already have right in front of you. So things like calculating the average salary in the marketing department or finding the exact percentage of employees who finished a training program. You're simply describing the facts of the data you have.
But what if you want to know what all of your employees think, but you can't possibly ask every single one? Well, that's where inferential statistics comes in. Here, we take data from a smaller, representative group, we call that a sample, and we use it to make an educated guess, or an inference, about the entire population. We're using a small piece of the puzzle to see the whole picture.
And this is a perfect way to see the difference in action. A descriptive question is super straightforward. What was the average number of sick days taken last quarter? We have all the data, we just have to do the math. But the inferential question, that's where things get interesting. Based on a survey of 500 people, what's the likely job satisfaction for all 10,000 of our employees? We're using a small sample to infer something about the whole group.
And that, of course, brings us right to our next section, the power of sampling. This is the critical bridge that makes all of inferential statistics work. It's all about how we use a small group to understand that big picture.
So how do you actually pick that small group? Well, you've got two main ways to go about it. Over on the left, you see non-probability sampling. Think of this as the easy way out, just grabbing the first 20 people you see in the cafeteria. It's quick, yeah, but the problem is it can be incredibly biased. You might just be surveying the engineering team because they always eat lunch early. But on the right, we've got the gold standard, probability sampling. Here, every single person in the whole population has a known, non-zero chance of being picked. It's the absolute best way to get a sample that truly represents the entire group. Let's actually walk through a great example of a probability method: systematic sampling. It's really simple but super effective. First, you get a list of everyone, say all your employees. Then you pick a random starting point on that list. Maybe it's person number 7. From there, you just pick every 10th person or every 20th, whatever your number is, and you just keep going until you've got the sample size you need. It's random, it's fair, and it's way easier than trying to draw 1,000 names out of a hat.
Okay, so we've got our data. We know how to gather it properly. What's next? Well, now we move on to Section 4, testing your big ideas. This is where we go from just having a hunch about something to formally testing it as a hypothesis.
When you're testing an idea with stats, you're always dealing with two competing hypotheses. First, you have the null hypothesis, or H0, This is the default, the status quo. It assumes there's no effect. For our example, the wellness program has no effect on stress. Then you have the alternative hypothesis, H1. This is what you're actually trying to prove, that there is an effect. The wellness program does affect stress. Think of it like a seesaw. The null hypothesis is balanced in the middle. Our job as data detectives is to see if our evidence is heavy enough to tip the scales and reject that default assumption.
And you can get even more specific with this. A one-tailed test is when you're making a bold prediction about the direction of the change. You're not just saying the program has an effect, you're saying the program decreases employee stress. A two-tailed test, on the other hand, is more open-ended. It's like saying, hey, I think the program changes employee stress, but you're not committing to whether it goes up or down.
So how do we actually decide if our result is a big deal or just random noise? This is where the science really kicks in. Analysts run a test that boils all the data down into a single score, like the z-scores you see here. Think of this score as a kind of surprisometer. Then we compare that score to a cutoff point we decided on ahead of time. That significance level, usually something like 5%, is just the amount of doubt we're willing to accept. If our score is more extreme than the cutoff, we get to say our result is statistically significant, meaning it's so surprising that it's probably not just a random fluke.
All right, so we can test ideas, but what about trying to predict the future? That's where we're headed next in Section 5, predicting workplace outcomes. We're going to look at an incredibly powerful tool called regression. Okay, before we dive into prediction, we've got to clear something up that trips a lot of people up: the difference between correlation and regression. Correlation just tells you if two things tend to move together. For example, as employee engagement goes up, productivity also tends to go up. But, and this is key, it doesn't say one causes the other. Regression takes it a giant step further. It tries to build a model to show how one variable can actually predict another. It answers the question, if we increase engagement by 1 point, by how much can we predict productivity will change?
Okay, I know what you're thinking. A formula. But don't worry about the symbols. At its heart, this thing is just trying to do one simple thing: draw the best possible straight line through a cloud of data points. Think of it as a recipe for describing the relationship between something like years of experience and salary. Let's break down the ingredients.
So here's how it all fits together. Salary? That's easy. It's what we're trying to predict. Now the coefficient, that's the magic number. It's the slope of our line. It tells us, on average, how much someone's salary goes up for every 1 additional year of experience. Then there's the intercept, which is just the theoretical starting salary at year 0. And that little error term at the end? That's just the model's way of being humble and saying, hey, experience is important, but it doesn't predict salary perfectly.
All right, we're heading into the home stretch. This brings us to our final section: errors, truths, and takeaways. Because no data detective's journey is complete without knowing what to watch out for. So when you're testing ideas, there are 2 big ways you can mess up. A type 1 error is a false positive. You get all excited, you claim your wellness program is a huge success, when in reality, it had no effect at all. A type 2 error is a false negative. This is when you miss a real discovery. You conclude the program doesn't work when it actually did. And honestly, in the business world, this type 2 error can be the more dangerous mistake. You end up abandoning a great idea just because your test wasn't sensitive enough to find the effect. So, after this whole journey, what are the big things to remember? First, statistics isn't just math, it's a language for finding truth in your data. Second, it's a journey that takes you from just describing what is to powerfully predicting what will be. Third, real success here requires both scientific rigor and that artistic nuance we talked about, because ultimately what this is all about is turning data into better, smarter decisions. And that really leaves us with the final and honestly the most important question of all. Now that we have this toolkit, now that we know how to listen to what our data is really telling us, how can we use this knowledge to build a better, smarter, and more equitable workplace for everyone? That right there is the real power of people analytics.